To be or not to be, that 'tis the question, whether 'tis nobler in the mind to suffer the slings and arrows of outraged fortune. And yes, I can keep going through that, but I won't. So this talk is probably a little different. And honestly, it started a while ago. But I'm going to start it off by the standard audience challenge. What's the difference between a mean, a median, and a mode? And looking around the room, I can see people immediately start going through their knowledge. And probably pretty close, about 75% feel like they know what a mean is. And about 50% think they know what a median is. And 10% can remember what a mode means. But if you remembered all three of them, let's do the extra credit question. What's the 9th Dedekind number? And we'll give you the answer to that at the end of this talk. So I'm Dave McAllister. I'm an open source technologist for a little company called NGINX. We were acquired by F5 in 2017. NGINX is an open source web server, load balancer, reverse proxy product, and about 40% of all internet traffic in the world run through NGINX on a daily basis. That's one of our 68 open source projects. And my job is to work around with all of those. But I've done another different talk, having a background in the observability space for a while. That was the data rules, the rules of observability. And in that talk, every single time, someone would come up and ask me to go deeper into literally one slide. And so I threw together this talk that was basically, let's look at the stats behind the numbers, what your software is telling you, and rapidly discovered that this is the most popular talk that I've ever written in my entire life. I've had it submitted 15 times. I've had 12 acceptances. And fortunately, it doesn't really matter, but hopefully will give you some things that you have never thought of before for this. I've been open source since before it was called open source. I started with Samba 2.0, Linux 0.93, way back in the dark ages. And since then, I've been really focused on, right now, monitoring, open telemetry, and the thing that if you haven't paid any attention to called WebAssembly, you need to learn about WebAssembly. So that's the shorthand version. So monitoring is a numbers game. And our numbers generally are time-stamped and they're key value pairs. So this is the metrics rules. Metrics are what the value is and what the value means in terms of this, and they're there. But data to be useful, we need to be able to aggregate it, we need to be able to analyze it, and generally speaking, we need to be able to visualize it. Those three things lead us into dealing with the statistics side of the house. So let's look at some of these questions that can come up here. How do you deal with outliers in your data? How do you recognize an outlier in your data? How do you know a representative value between two different types of data? In this case, I'm pointing out that speed and rate are not the same thing. And you may think of them the same way, but they actually get treated different when we look at it on a statistical basis here. And then, how do you represent rate of change? Because there are different ways of representing rate of change. What is your dashboard telling you about that data? So when an alert occurs, do you really know what it means? So let's start by defining a couple of things. So I've got, I think, 61 data points up here. And a mean is the central tendency. It represents the average value of a set of data. Quite few of us talk about them as averages. In Excel spreadsheets, you find an average, you don't find a mean. The median is the middle value of a sorted data set. So sort your data, pick the one in the middle. If it's an even number, add the two together and create an arithmetic average for that. And the mode is the one that appears the most often. And in this case, my mean is 5.444, my median is 6, and my mode is 1. Or is it? So, in this case, is it 4.13? Is it 2.79? It matters. Remember that first question I asked you? Define a mean, a median, and a mode? Well, there are actually lots of different means in the world for this. So the one we're most familiar with is arithmetic, but there's a harmonic mean, a geometric mean. We can have trimmed means, we can have weighted means, we can have moving means. We can have k-means, which are part of a grouping structure. What are the means around our group points for this? Each of these has its own particular use. Each of these is implemented in monitoring software on almost all cases. K-mean is the one that's kind of fuzzy at this point. Every one of them will give you a vastly different result for this. And what it does is to make like and unlike comparisons easier. So this one, when I said what does it mean, this is probably what every one of you thought of, is an arithmetic mean. Add the numbers together, divide by the number of items in there, and that gives you this arithmetic mean. This, by the way, is a central point in a normal distribution curve, but it is not necessarily the 50% point. It is only the 50% point if your mean is 0 and your standard deviation is 1. And that's why it can be very useful to understand the differences here between when we're moving into this space about what the 50% point is and what the middle point, the mean point is for this. And it's generally used for comparing to previous conditions. So we find an average, we figure out, and then we look at the next number and see where it compares to that average value for that. And in time series, we tend to do this as a continual flowing process. We either move them as blocks or we continually add the new items to them. This gets us into a scale problem for that. But in this case, I'm looking at a load balancer. My load balancer is got 2K of a possible 5K, 300 of 1K. You can read the numbers here. And the arithmetic mean simply says how many requests per second is going into this, divided by 3, and I have 13.33 requests per second. Very simple, very straightforward. Is it useful? Well, the interesting aspect is that arithmetic means will always give you the highest possible value in a mean. And when we look at a geometric mean, it has a very different, slightly more complex and challenging mathematics for this. In this one, we multiply all the numbers together and we take the nth root. Until computers came along, nobody went past about a third level geometric mean, finding a cube root. But for instance, finding a geometric mean of 1,000 items means finding the 1,000th root of that mean, that number that gets calculated out. It can get really hairy really fast. Computers are fast enough to do this. When we look at it from a DevOps, the SRE relationship here, it looks at things like what's our deploys per unit of time? Because these are vastly different and can be vastly structured in different ways. And they change, interestingly enough, exponentially. We tend to maybe put them out in a linear format, but the actual mode of change is exponential. So if you're looking at exponential or you're looking at changes where the changes are varying, this is really good. MTTR, mean time to repair, or throughput. Similar problem up here. I'm looking at a load balancer structure. Doing the structure, geometric mean works out to 6.52 requests per second. And if you remember, the other one was 13.33. Which one's right? Well, the interesting thing is what this is actually showing you is what this would look like if you were running on a single computer with all that capacity. And so if you built a single computer that could run the 6,600 requests per second, you'd actually only be using about 6%, 6 to 6.5%. So this gives you an indication of what your actual use pattern is, that the arithmetic mean more than doubled or roughly doubled. So geometric means are really useful when we're trying to accrete other things together so that we can look at what it would look like as a single stable environment. Now, the last one is harmonic. And harmonic means are take the reciprocals of all those numbers and then divide that sum into the number of items that you're dealing with. And once again, this DevOps engineering space here, it's performance within a range. So this one tends to float as the lowest point, sorry, for this. And it is an indication of latency. It's very useful in telling you what the behavior structure is going to look like. It is incredibly useful when you're looking at more complex environments. And by the way, it helps you find outliers. So using the harmonic gives you some really great information about what your outlier structures look like. So slightly different model. I have 4 computers. They're running at current loads here. Its harmonic mean is 19.19. However, if one of them peaks up here, and all of a sudden it moves up to 80%, my node 4 moves to 80%, my node 3 dropped to 10% here, all of a sudden I'm now at 32. And so once again, I'm now looking at and seeing what my overall use, as if this was a single environment. My throughput numbers have changed for the structures. My harmonic means give you some really cool data. Catch, sorry, hate to do this to you, because I really like talking about these. There's a problem with both the harmonic and the geometric mean. You may not have the number 0 in your data set. Taking a reciprocal of a 0 gives you infinity, or gives you an undefined. You can't use that. Taking it for a geometric means you're multiplying by 0, then the result is 0, and who cares what number of roots you take, because your answer is going to be 0 or undefined. And so when you have data that you can drop the zeros, it's incredibly useful. But you need to understand that there are limitations around that structure. And by the way, anytime you're working with something that has a peak value that has jumped the level it has, this 10% to 80%, there's always some risk in the actual statistics showing you what you're looking for. So, median. Incredibly underused. And this, by the way, is the topic that caused this talk to come into being, was a discussion around median structures. It's the center value of a sorted list. Again, sort your list, take the center value. You're done. And unlike the mean, the arithmetic mean, the median is always the 50% point in a normal curve. Most things do wrap out to normal curves. And what happens, though, is that they tend to track themselves, and after they stabilize down, you'll notice they're actually pretty close. Here's where it becomes interesting. When we start looking at structures around that, the median will give you some really great outlier information. And the outlier information looks kind of like this. First of all, this is called a measure of variability. And the measure of variability says how my numbers behave. If I give you the number, the mean is 23, you don't have a lot of other information. If my range is 20 points, that means that my mean, 50% point here, has 10 points below and 10 points above. And so you now have a value point that comes into play. We see this a lot where we're looking at the structures in this. But there are lots of other pieces. Standard deviation is the one that's probably the most common. But this thing called IQR falls into this category that is helps us target outliers. There's this rule of thumb called the outlier formula. And the outlier formula says you take the Q3 point, break your data into 4 pieces. The Q1 point is the variance between right after the 25% point. Q2 is the middle. Q3 is the 75. Subtract the Q3 from the Q1, and you get this interquartile range. This is the vast majority of your distribution curve. And what then happens is that you take the structure, the IQR, this is the visual model for this, that IQR is that middle piece. You multiply the IQR by 1.5, and you'll end up with the structures. IQR below Q1, taking that structure, everything to that left would be considered an outlier, everything to this right would be an outlier. In short, there are dragons out there using the old-fashioned map structures. That gives you a very quick way of determining whether you are in an outlier situation or not in an outlier situation. Depending on your use of data, either outliers are something you want to alert on, or there's something you want to ignore, depending on which way your data is moving. So, missed the button for this. So I just said, for instance, that we can have this mean and median construct. The difference is that the median does not change drastically over time. After it is stabilized out, when you add a new data point to it, the median doesn't change. It may move by 1 point, but the mean can jump drastically. This means that when you're looking at alerts, if you are dependent on the data being stable, you expected the data point to be always at a particular point, the median is stable value. And in historical analysis, when you're looking at things like everything that's happened last Thursday and the previous 6 Thursdays, the median will actually give you a stable viewpoint. Because when you've jumped to this mean basis, your mean does not go back down to your median point. It will slope back down over time if it returns to the values. This means that when you are looking at alerting structures, if you're looking at a baseline stability, use the median. If you're looking at comparisons to the current state of the world, use the mean. But keep in mind that that will massively impact your alerting structures. You may miss alerts or you may get more false alerts based on what your structures look like. So see this a lot in things like anomaly detection or response time monitoring, where things expect to be stable. We expect response times to be in, I don't know, minutes. We expect e-commerce things to go through in 3.7 seconds. If you have a jump, your alerts will no longer work. And by the way, just because I decided to do this, this is what it would look like with harmonic in there. And again, you can see, for instance, that the mean and the harmonic are different. Keep in mind that the harmonic is always the lowest value you'll see inside of that. The mean and harmonic move a little bit, but the mean has a pretty good jump inside of here for a single point outlier. Harmonics, no zeros. By the way, if you're using one of the p-values, p50, p90, p95, congratulations, you're already using the mean. It's just a shifted mean. And calculating a p-value, very honestly, take that same sorted list, count the number of items that you have in there, multiply it by your 95 value, and then count the number of items, and that'll give you your p95 point. It's very simple, very straightforward. So strongly recommend looking at those. Okay, mode, the last of the big three here. Most common recurring item, and interestingly enough, not usually used a lot in day-to-day active DevOps. It's inferential. We'll see this show up, for instance, in log analysis or possibly security monitoring. We'll also see it show up in behavior monitoring a lot. So this will tell you that certain things are happening recurring. In observability space, for instance, we know that basically when we see bad tracing, it's pretty much down to 5 or less items causing the same problem every single time. No matter how many items there are, it's about 5 for that. Those 5 will pop out on a mode chart. You'll see them as the extended model for that. And log analysis, it's really an essential piece to help identify, again, what's common in our pathways. So the mode is really straightforward. Again, count everything, sort everything, count the numbers that are there, and it pretty much comes out. The nice thing is every single piece I've talked about, by the way, is built into every piece of monitoring software I've ever seen. And so we don't use them very often, but they're all there because we tend to default to the common default characteristics. Slight sidetrack here because I just mentioned inferential. There's 2 concepts that show up in stats. One of them is descriptive and one of them is inferential. Descriptive says use every single piece of data to make your number appear. Inferential says pick the sampling of the data that you want. So use the set of data that you've chosen to use to find what your values look like here. They're both used for visualization. We find a lot more things used in descriptive for visualization because it's easy to track the trends in descriptive. We're not biasing our own results for that. Inferential samples the data. The samples are used to draw conclusions. And so it's used to test against ideas or predictions that things we think might lead to this. It visualizes, but that sampling thing can be a real pain. So monitoring does have this data problem, and that's the fact that we have a whole lot of data. Back when I was working with a company called Scalar, which does log search, the largest data set we ever ran into was a company that produced 43 terabytes of log files on an hourly basis. Imagine how big that data set is. They wanted to add tracing to it, and the number went up to about 92 terabytes per hour. You cannot deal with that much data. You have to sample, unfortunately. And so we start aggregating these segments. We start aggregating the samples down a little bit to provide some other pieces. And there are multiple kinds of sampling. There's this random sampling model, stratified, cluster, semantic, or purposeful standards. In my space, in this observability space, it really breaks down to kind of two basic types. One's called head-based sampling and one's called tail-based sampling for that. Head-based sampling says, when I start, I'm going to just randomly pick things. I'm going to sample the first one here and the 15th one and the 27th one. I have no idea what the results are. The second side, tail-based sampling, says I have certain criteria, and at the end of this, when I know what the results are, I will then sample that meet the criteria. In short, tail-based sampling isn't really sampling. It's actually you're defining and filtering versus sampling. So it's a misnomer and a misnamed environment for that. But in a head-based sampling, given this as my sample trace here, I've got all these different things here, but when I sample it, I see that I've got a time that's at 1.2 seconds, and I have one little error that shows up. When I look at the entire descriptive data set here, I actually have lots of little errors that are showing up here, and I have traces out here in the 29 to 40% range. And so this is where sampling can start giving you some real bad problems here. It changes your behavior from descriptive to this inferential model here, and it can hide outlier behavior. So when we start looking at doing this, we need to be aware that we may not be able to see all the data or be able to backtrack to all of the data that's involved in that. Therefore, maybe a combination of a certain amount of head-based and tail-based sampling is the best approach, or maybe keeping a differential set for 15 minutes, which turns out to be roughly the arithmetic average of how long it takes to do a forensic study on a bug of data. But it's a necessary evil. We just cannot deal with that much data. And that leads us into descriptions, or distributions. And most of us are familiar with normal, but there's lots of distributions here. Beta, you may be familiar with, well, probably more commonly called for you, A/B testing. So it's a one-to-one comparison of two items for that. A couple of interesting ones that I want to talk about. Weibull is one of them, and I'll talk a little bit. But again, slight sidetrack on this thing around standard deviation. So again, variability measures the variability. It identifies trends and outliers, but it identifies trends and outliers in a normal distribution model. If you do not have a normal distribution, standard deviation is useful, but not meaningful for that. And by the way, it is never a percentage base. It's only if you make it into a percentage that it becomes percentage based. But in a standard distribution, 68% of the data live within a one standard deviation plus or minus, all the way out to 3 out plus and minus, so 6 items here at 99.7%. And so you could easily calculate the distribution or the standard deviation, use 4 times this, and hit your 95% mark. And it's easy to keep this as a running total. It's very easy to keep this math going forward here. Lead times, recovery times, anomalies and alerts, where they fall into these things. But you also see standard deviation used a lot in SLO, SLI measurements. So, new distribution, probably to a lot of you here, is called Weibull. Weibull is time to failure. And this is a very simple example, and I admit it for this. Don't ask the math. The math is another 3 or 4 pages of stuff, and I don't want to go into that for this. But R, fortunately, has all these little cool things that you can just call and do Wable. And by the way, things like Datadog or Splunk or Elastic, I believe, all allow you to make R calls. And so you can just call off to an R routine and actually produce this. In this case, you can see over here, I've got some items here. The disk drives fail after 500 hours. The standard disk drives, the solid state drives, 2,500 hours. And I want to know what my chances are of having a failure occur in this case, 3,000 hours. And it turns out when I run this through here, the odds of something failure occurring is roughly 30%. And that's an interesting piece of information because it is taking into effect that you've probably had a failure beforehand. But at 3,000 hours, you're probably going to have a 30% chance of a failure. And so interesting distribution for you to be able to do forecasting on when things fail. If you have data on software errors, Wable will actually also do that type of structure as well. And will start giving you indications of where you might see other things. Exponential is the other one I want to touch here. And this one is about sort of the rate of things. So exponential in this case, I'm looking at user request arrival times. And we've got 120 that came in at 5 seconds down to 10 coming in at 20 seconds here. We use this in network performance a lot. We see this in user request messaging services, MQTT or AMQP, one of those. Again, RASC will do this for you. The math is quite hairy. And I just make my R calls here. Using that model, I can say that my rate is 0.42. And if I say, what are the chances of me seeing a message come in 10 seconds? And the odds are roughly 40%. And so this will give you the baseline for looking at your messaging as alerts to be able to say, do I have outliers in my messaging structure? Okay, side pet peeve time. This is a common statement in our industry, that statistics on scale are not your friend. And it's wrong. The issue is that probability on scale is not your friend. The probability states the odds of something going wrong. Statistics will help us determine what that probability is, but statistics just measure and give us an indicator. Probability indicates an action that could occur from something. So if you have a 1 out of 10 chance of something happening, that's not a statistic, that's a probability curve. And so this is something that's showing up a lot, and sorry, it's pet peeve. You can completely ignore me on this, but honestly, it just drives me up the wall a little bit. Okay, so some common pitfalls here. Ignoring scale. So if you are showing something and your scale is 1 to 10 on one side and 1 to 50 million on the other side, and you put them on the same graph, the scales don't match and they are not meaningful. If you're showing a 20-point difference between something between 130 and 150, and a 20-point difference between something that's 30 and 50, scale matters. We see this commonly, people ignore scale for this. Looking at the wrong central measure. We talked a little bit about this. Looking at means when you should be looking at medians. Looking at medians when you should be looking at means. We'll get to the next one, confusing correlation with causation. I'll talk about that in a minute. Failing to see biases. And this shows up in sampling a lot. You tend to choose the things that you know could go wrong, but that means you're missing all the things that you don't know could go wrong. So we have biases in that data set here. And then getting causation backwards is my fifth one on this one. And it's an interesting structure. So causation versus correlation. This is number of letters in the winning words in the U.S. Scripps National Spelling Bee correlate almost exactly to the number of people killed by poisonous spiders in the U.S. Okay. And I mean, if you just look at the curve, you'd go, oh my God, I hope they never have anti-disestablishmentarianism show up as a word because we're going to have a lot of people dying from spider bites. There's no correlation. The number of movies that Kevin Bacon appears in and the number of people who die in swimming pools is an almost exact correlation. There's no causation I know of. I've seen some of his recent films, so maybe there is. But nonetheless, keep that in mind. For instance, that last bullet I talked about for this one, getting causation backwards. The common example for this is we know that there is a correlation between people drinking heavily and depression. But what is what? Does drinking cause depression, or does depression cause drinking? Well, y'all are all SREs. You're here at an SRE conference. We all know that end users cause depression and drinking. So keep that in mind. And so I want to do a quick summary here. Statistics are how we analyze our metrics, and we use that to build our aggregations and to build our visualization. Most choices we make use very few of these things, but understanding the reasoning behind it and what they really mean can be really useful. And sometimes using other things can be very meaningful and give you clear insights into your data. There's a lot more that can be covered in this space. We can talk about p-values and the null hypothesis. We can talk about Bayes' theorem, conditional probability, or why the Price is Right in the US had 3 doors, and why if they opened one door, you should switch your choices for this. The data manipulation, how people manipulate their data to get the results that they want for this. Visual miscues, how we visually misrepresent our data structure. You have to wait for the next time for that. And I want to finish with my favorite quote, because it applies to everything that we all do here. The most effective debugging tool is still careful thought, coupled with judiciously placed print statements. Brian Kernighan wrote this, Unix Beginners, for 1979, and it is still useful today. And the 9th DD-kind number is this, 42 items long. And basically, a DD-kind number measures the number of mononodal intersections that can occur. So if you have 9 different blocks across, it's a 42-digit possible pathways through there. So with that, I'd like to thank y'all for listening to me today. You can find me on LinkedIn. You can find these slides on GitHub. And if you really want to chat, the NGINX open source community is there as well. Thanks. Enjoy the rest of the show. And I'll place my bet right now. I've never had a question.
Yeah, probably. Is David with us? Yeah, okay. So there's a slight change in the program. After David, it should be Ant, but you can come. But we will have Rogero and his colleague. I forgot the name. Yeah. Talking right after. Yep. All right. So let's get plugged. You have a question? Oh, yeah, question. So I'm coming.
I've never had a question. I don't know how to handle this. The pressure.
Here we go. So
yeah, sorry,
it's recorded.
I cannot. So yeah, it's real quick. So let's say nobody wants to admit this, but let's say if you're really, really bad at math and you work as an SRE and worse in observability, what should you do to, let's say, make better sense of your data? Just by looking at your presentation, I found like a new universe out there. And yeah, should I study on it, or should I make my manager send me to trainings, or?
No,
Yeah.
there's I can't remember the name of the book, but there's I think it's called Statistics for the Rest of Us. It's a very straightforward, very simple, clear-cut description of almost everything I talked about. And if you're interested in looking at the sampling, there's a open telemetry book called Practical Open Telemetry, which has the single best description of sampling that I have ever seen in my life by Daniel Blanco.
Is that O'Reilly?
Yeah. No.
No.
A-Press.
Okay.
So we have one in the back there. But yeah.
I
Take a look at the guide to statistics. I actually find it just enjoyable reading. I handed it to my wife, who doesn't tend to like to read things like that. And it is just fascinating going through this and going, oh, so that's what that meant. So really useful.
Thank you.
First of all, thanks for your talk. I really loved it. I loved it, and it reminds me of talks about performance engineers where we look at the outliers instead of the stuff. I was more interested on the sampling stuff because when you look around with the first customers using OpenTelemetry, as of now, they are the ones setting the sampling, and some people says I don't want to spend much money, so I'm going to put a 1%, 2%, and which I think it's a mistake, like you mentioned. Do you think that we should have a dynamic sampling where the system that stored the data sees that there is no deviations or it's standard, nothing's changed, so then you can reduce the sampling rate. And then once there is a difference in the value, then you can adjust to say, give me more data, so then we have a more accurate view of the data coming in the system.
Actually, what you just described is pretty close to what I would recommend, having done this for a while. I call it purposeful sampling. And it depends on what your use case is looking like. If you are trying to debug problems, we know that basically 15 minutes of descriptive data will tell you where and what the problem exists. And so save everything for 15 minutes. Treat it like a log rotate problem. And just literally save everything for 15 minutes. At the end of 15 minutes, save the metrics for the entire set and save what we would use as tail-based, things that have triggered our alert structures. That will give us me two things. I can always go back and look for things, the unknown unknowns that I didn't know could occur. It will also let me record and monitor the things I know that did go wrong and how they improve in the future. The reason I'm saying it's a little use case is if you're using observability techniques for security reasons, you need 2 years of data, not 15 minutes. And therefore, you're probably just going to do sampling from a tail-based approach of saying, you triggered something, I'm going to save you. So metrics are not hard to save. Metrics are small. Timestamp, key value pair. It's when we get into logs and traces, and now when we get into profiling, that's going to be more of a challenge.
I agree. So I guess now there's no sampling decisions based on what you described. So do we have to wait until OpenAMP is fully implemented on all the OpenTelemetry SDKs?
Yeah, there are some people working on this purposeful sampling, and there are certain monitoring tools that have this partially built in. So, by the way, I do not work for a monitoring company at this point in my life. But for instance, Honeycomb has this concept for saving events for a period of time and then structuring them down. I'm not sure my viewpoint is quite complete enough, but it's there. OpenTelemetry actually builds in the ability to do head and tail-based samplings. So that's really straightforward and very simple to deal with.
Thanks.
Sure. There's one behind you.
Great presentation, by the way. I have a question. Like, I think it is slide number 4, which has a load balancer in front of it. You showed 3 nodes and load balancer in front of it, right? I can see there is uneven distribution of requests, right? And if there is an uneven distribution of requests, there has to be something with the algorithm, right? So why in the slide you are calculating number of requests per second as per the nodes? Why not on the load balancer? It's actually make more sense on the load balancer rather than the nodes.
So it was partially a deliberately constructed item. However, when you're actually doing load balancing, your job is not to meet the maximum load balancing. Your job is to actually load balance across the board so that your structure matches appropriate traffic requirements. And depending on the nature of your structure, if you are doing a rolling structure, this one gets this one, this one gets this one, this one gets this one, this one gets one, this one gets one, it's less of a problem. If your load balancer structure is similar to the way that we treat them, small project base here, where it is actually firing off separate worker structures for this, you want to go to the minimum structures because otherwise you're going to be burning CPU and memory that you don't need to burn. And so using a lower model for that gives me actually a more accurate load balancer result to my computer structure. It may not give me, purely the load balancer, but load balancers run on something. And so we want to minimize that structure, and using that one will give you a lower structure for minimizing your infrastructure resources.
So, as per what you told, I think.
This is what happens when I do a 30-minute talk versus the 1-hour talk.
So basically, this has happened between the workers, right? So within the same program.
Yep.
So that in terms doesn't define nodes, that define workers. So
Right.
you're actually calculating on workers rather than the nodes.
Right.
And that's how NGINX also distributes.
Yeah,
Right?
that's how NGINX serves out
Yeah,
pieces
I got
for
it.
that.
Yeah,
But yeah, the
that's-
load balancer is a slightly different model, but it's similar.
Yeah. Cool.
Thanks again. I'll turn this over to my next speaker.
Thank you.